Welcome! Today, we'll dive into an engaging problem, problem number 1599, maximum profit of operating a Centennial wheel. We'll explore the scenario, break down the approaches considered, and arrive at an efficient solution. Let's get started. In this problem, you own a Centennial wheel that has 4 seats per gondola. The wheel operates on a counterclockwise rotation, and each rotation takes 1 unit of time. However, each time the wheel rotates, it costs you running cost dollars. Customers waiting to board the wheel pay boarding cost dollars each when they get on. Importantly, you can only board up to 4 customers per rotation. If fewer than 4 customers are waiting, then all of them board during that rotation. The challenge lies in deciding how to maximize your profit. To calculate profit, you subtract the total running costs from the revenue generated by boarding customers. Your goal is to determine the maximum profit you can achieve and the earliest rotation at which this maximum occurs. If the profit never becomes positive, you will return -1 instead. The input includes the array customers, which tells you how many customers are waiting at the beginning of each time unit, as well as the boarding cost and running cost. The output will be the rotation number where the maximum profit is first achieved or -1 if the profit remains negative. Let's look at some examples to understand the problem better. In the first example, we are given customers equals 8, 3, boarding cost equals 5, and running cost equals 6. On the first rotation, 4 of the 8 waiting customers board the wheel, leaving 4 still waiting. The profit for this rotation is calculated as 4 times the boarding cost, which is 20, minus the running cost of 6, resulting in a profit of 14. On the second rotation, 4 more customers board, leaving 3 waiting. The profit from this rotation adds another 14, making the total profit 32. On the third rotation, the remaining 3 customers board, and no one is left waiting. The profit increases by 9, bringing the total to 41. The maximum profit of 41 is achieved at rotation 3. Therefore, the output for this example is 3. Now consider the second example, where customers equals 10, 9, 6, boarding cost equals 6, and running cost equals 4. In the first rotation, 4 out of the 10 waiting customers board, leaving 6 behind. The profit for this rotation is 4 times the boarding cost, which is 24, minus the running cost of 4, resulting in a profit of 20. In the second rotation, another 4 customers board, leaving 2 still waiting. This adds another 24 minus 4 to the profit, making the total 44 so far. On the third rotation, the remaining 2 waiting customers board, and no one is left. However, new arrivals from the customers array keep adding to the queue, and further rotations continue to increase the profit. By the 7th rotation, the profit reaches its maximum of 82. Hence, the output here is 7, which is when the maximum profit is first achieved. Finally, let's examine the third example, where customers equals 0, 0, 0, 0, boarding cost equals 10, and running cost equals 4. In this scenario, no customers ever arrive to board the wheel, so the revenue remains 0 for every rotation. However, the running cost of 4 is incurred for each rotation, meaning the profit decreases with every turn of the wheel. Since the profit never becomes positive, the output for this case is -1. The constraints of the problem also highlight edge cases to consider. For example, if there are no customers at all, the profit will always remain negative. The algorithm must also handle large input sizes efficiently, as the customers array can have up to 10 to the power of 5 elements. Additionally, scenarios where the boarding cost is high and the running cost is low will lead to quicker profit maximization. These considerations are critical to solving the problem effectively. To solve this problem, we first consider the brute force approach. The intuition here is straightforward: simulate every rotation of the Centennial wheel step by step. The wheel has 4 seats, so each rotation can accommodate up to 4 people. Given the customers array, which represents the number of people arriving at each time unit, we track the customers waiting and those carried over after each rotation. For every rotation, we board as many customers as possible, calculate the profit for that round, and keep track of the maximum profit in the rotation where it occurs. The simulation continues until there are no more customers waiting or carried forward. Now, a few key observations: each rotation has a fixed cost, called running cost, and each boarded customer contributes to the profit, represented by boarding cost. The objective is to maximize the net profit, which is the total boarding profit minus the cumulative running cost. While this approach is simple and intuitive, it can become inefficient for larger inputs, as we simulate each rotation exhaustively. Analyzing the brute force approach, we find that its time complexity is O, n plus k, where n is the length of the customer's array and k accounts for the extra rotations needed to clear any carryover customers. The space complexity is O, 1, as only a few variables are used to track the state. Building on this, we can design an optimized approach that reduces unnecessary calculations. The optimized solution still tracks the carryover customers but adds two key improvements. First, it efficiently manages carryover customers by incorporating them into the next rotation. Second, it incorporates an early stopping condition. If the carryover customers are insufficient to generate a profit higher than the current maximum, we terminate the simulation early, avoiding redundant iterations. This refined approach uses variables to accumulate profit dynamically, update the state efficiently, and track the rotation that achieves the highest profit. A critical observation here is that the main computation revolves around calculating the number of boarded customers and carryover customers each rotation, a task that remains efficient when early stopping is applied. The optimized approach has a significant advantage in terms of complexity. Its time complexity is reduced to O, n, where n is the length of the customer's array. This is because the carryover customers are handled in a single pass, without requiring additional iterations. The space complexity remains O, 1, as no additional data structures are needed. Now, why choose the optimized approach over brute force? While the brute force method is easier to understand and implement, it becomes inefficient for large inputs due to unnecessary iterations. The optimized approach, on the other hand, minimizes these iterations and focuses only on meaningful rotations, making it faster and more scalable. There are trade-offs to consider. Brute force is simpler but slower, while the optimized approach is slightly more complex but significantly faster. A key insight, or aha moment, in developing the optimized approach is recognizing that the carryover customers directly impact profit. By identifying when further rotations would no longer contribute meaningfully, we can terminate the simulation early, ensuring both efficiency and correctness. The optimized approach stands out as the most effective strategy, striking a balance between simplicity and efficiency. It guarantees correctness while being capable of handling edge cases, such as scenarios with a large number of customers or multiple carryovers. This approach ensures that profit is maximized without violating performance constraints, making it both scalable and practical. By focusing on early stopping and efficient carryover management, we avoid unnecessary computations and ensure that every rotation contributes meaningfully to the profit. Ultimately, this method not only addresses the problem requirements but also demonstrates a robust design that adapts well to different input sizes and complexities. In this problem, we are tasked with maximizing the profit from running the Centennial wheel. The wheel has 4 seats, and each rotation can accommodate up to 4 passengers. We are provided with an array called customers, where each element represents the number of people waiting to board the wheel at a specific time unit. Additionally, we know the ticket price per passenger, denoted as P, and the operational cost per rotation, denoted as Q. Our goal is to determine the maximum profit achievable and the rotation at which this profit occurs. To solve this, we start by clearly defining our problem. The input includes the customer's array, ticket price P, and rotation cost Q, and the output is both the maximum profit and the rotation number. Next, we initialize key variables. The current_profit variable will track the cumulative profit during the simulation, while max_profit will store the highest profit encountered, and best_rotation will record the corresponding rotation number. Additionally, we use a waiting_queue to manage leftover customers who couldn't board the wheel during previous rotations, ensuring these passengers are accounted for in subsequent rotations. The next step is to simulate the operation of the Centennial wheel across multiple rotations. For each rotation, we first handle the boarding process. New arrivals at time I from the customer's array are added to the waiting_queue. Passengers are then boarded, up to a maximum of 4 per rotation. If fewer than 4 people are available in the queue, we board as many as possible. The waiting underscore queue is updated to reflect any remaining passengers who couldn't board. After boarding, we calculate the profit for the current rotation. The revenue is determined by multiplying the number of passengers boarded by the ticket price P, while the cost is a fixed value Q. The current underscore profit is updated by adding the difference between the revenue and the cost. To ensure we track the best possible outcome, we compare current underscore profit to max underscore profit. If the current underscore profit exceeds max underscore profit, we update max underscore profit and record the current rotation number in best underscore rotation. Finally, after processing all rotations, we handle any leftover passengers in the waiting underscore queue. The wheel continues operating until all customers are served, provided it remains profitable to do so. For these additional rotations, we follow the same steps of boarding passengers and calculating profit, but we stop as soon as operating the wheel no longer increases the current underscore profit. Several key insights emerge from this approach. First, boarding up to 4 passengers per rotation is the most efficient strategy because it maximizes immediate revenue while adhering to the problem's constraints. Second, the wheel should only operate when the revenue from passengers exceeds the operational cost, ensuring no rotations result in a loss. To guarantee we don't overlook the optimal solution, we maintain a running max underscore profit and best underscore rotation, which allows us to identify the best outcome without revisiting prior calculations. It's also important to consider edge cases. For instance, if the customer's array is empty, the profit will naturally be zero, as there are no passengers to board. Similarly, if the operational cost Q exceeds the revenue from 4 passengers, operating the wheel will always result in a loss, and the best strategy would be to avoid running it altogether. From a data structure perspective, the customer's array keeps track of new arrivals at each time unit, while the waiting underscore queue efficiently handles leftover passengers in a first-come first-served manner. Variables like current underscore profit, max underscore profit, and best underscore rotation are essential for maintaining running totals and ensuring the solution is both accurate and efficient. Now let's analyze the complexity of this algorithm. The time complexity is O, n, for iterating through the customer's array, where n is the number of time units. Additionally, there's an O, k, component for processing leftover customers in the waiting underscore queue, where k represents the total number of waiting passengers. Therefore, the overall time complexity is O, n plus k. For space complexity, the worst-case scenario is O, n, which occurs when all customers are waiting in the waiting underscore queue. To better understand the algorithm, let's walk through an example. Suppose we have an input of customers equals 8, 3, 0, 5, with p equals 5 and q equals 6. In the first rotation, there are 8 new customers. We board 4 passengers, leaving 4 in the queue. The revenue is 20, the cost is 6, and the profit becomes 14. In the second rotation, 3 new customers arrive. We board 4 passengers, including 3 from the new arrivals and 1 from the queue, leaving 3 in the queue. The revenue is again 20, the cost is 6, and the cumulative profit is 28. In the third rotation, there are no new customers, so we board the 3 passengers from the queue. The revenue is 15, the cost is 6, and the cumulative profit is 37. In the fourth rotation, 5 new customers arrive. We board 4 passengers, leaving 1 in the queue. The revenue is 20, the cost is 6, and the cumulative profit reaches 51. From this example, we can determine that the maximum profit achievable is 51, and it occurs at rotation 4. This result highlights the importance of carefully managing the waiting underscore queue and making decisions based on the profitability condition. By consistently tracking the running profit and ensuring the wheel operates only when it is advantageous to do so, we can effectively maximize the profit over the given period. This concludes our algorithm deep dive into the maximum profit of operating a Centennial wheel problem. The provided Python solution efficiently calculates the maximum profit from operating the Centennial wheel. First, the inputs include the customers list, which represents the number of customers arriving per time unit, and the costs for boarding and running the wheel. The function initializes variables to track waiting customers, total boarded customers, maximum profit, and the corresponding rotation at which maximum profit occurs. The loop continues until there are no customers waiting and all time units from the customers list are processed. In each iteration, new arrivals, if any, are added to the waiting queue. The wheel can board up to 4 people per rotation, so the minimum of 4 in the waiting queue size is boarded. The waiting queue is updated accordingly, and the cumulative number of boarded customers is updated. The profit for the current rotation is calculated as the revenue from tickets sold minus the running cost. If the profit exceeds the current maximum profit, the maximum profit and the corresponding rotation number are updated. Finally, the function returns the rotation number that produced the maximum profit if the maximum profit is positive, otherwise, it returns -1. This ensures that the solution accounts for scenarios where operating the wheel is not profitable. Here, we begin by defining the solution class and the method min_operations_max_profit. This method takes 3 parameters: an array of customers representing the number of people arriving in each rotation, the boarding cost per customer, and the running cost for each rotation of the wheel. We initialize several variables to track the state of the operation. N is the length of the customers array, waiting keeps track of the number of customers yet to board, total boarded accumulates the total number of customers who have boarded, max profit stores the maximum profit observed so far, and max rotation records the rotation that achieved this maximum profit. The rotation variable counts the current rotation of the wheel. The while loop runs as long as there are waiting customers or we haven't processed all the rotations in the customers array. In each iteration, we first account for new customers arriving during the current rotation by checking if the current rotation index is still within the bounds of the customers array. If it is, we add the number of customers arriving in this rotation to the waiting variable. Next, we calculate how many customers can board the wheel, with a maximum capacity of 4 per rotation. We update the waiting and total boarded variables accordingly. Then, we compute the profit for the current rotation using the formula, total boarded * boarding cost, rotation plus 1 * running cost. If this profit exceeds the current max profit, we update both max profit and max rotation to reflect this rotation as the new maximum. Once the profit calculation and updates are complete, we increment the rotation variable to move to the next cycle. This continues until all rotations are processed and there are no more waiting customers. Finally, after exiting the loop, we check the value of max profit. If it is greater than 0, we return max rotation, which indicates the rotation that achieved the highest profit. Otherwise, if no profit was made throughout the process, we return -1. This ensures the function handles cases where the operation is not profitable. By following this approach, we efficiently calculate the optimal rotation to maximize profit while managing the constraints of customer arrivals and the operational cost of the wheel. Here, we start with a basic example where the input consists of 2 customer groups, 8 in the first group and 3 in the second. The boarding cost is 5, and the running cost is 6. Initially, no customers are waiting, no one has boarded, and the profit variables are set to track the best rotation. In the first rotation, all 8 customers from the first group arrive, so we add them to the waiting queue. Since the wheel can board a maximum of 4 people per rotation, we board 4 customers, leaving 4 still waiting. The profit for this rotation is calculated as 4 times the boarding cost, minus the running cost, which gives us a profit of 14. This becomes our current maximum profit, and we note that it occurred in rotation 1. The rotation counter is then increment for the next set of calculations. Now, in the second rotation, 3 more customers arrive, adding to the 4 already waiting, making a total of 7 in the queue. Again, we board 4 customers, leaving 3 still waiting. The total number of boarded customers is now 8. The profit for this rotation is calculated as 8 times the boarding cost minus the cost of running the wheel twice, which comes out to 28. Since this is higher than the previous maximum profit, we update our maximum profit to 28 and note that it occurred in rotation 2. Moving to rotation 3, no new customers arrive, and the 3 waiting customers are all boarded. The total number of boarded customers becomes 11. The profit for this rotation is 37, which is now the highest profit we've seen, so we update the maximum profit to 37 and note that it occurred in rotation 3. The process ends here as all customers have been boarded, and we return the rotation number that gave the maximum profit, which is 3. In this example, we focus on a case where the profit is relatively small due to lower boarding costs and higher running costs. The input consists of 3 customer groups, each with 2 customers, a boarding cost of 4, and a running cost of 5. Initially, all variables are reset to 0. In the first rotation, 2 customers arrive and are immediately boarded since the wheel can accommodate up to 4 people. This results in a profit calculation of 3, which becomes the maximum profit so far, with the corresponding rotation being 1. The rotation counter is then incremented as we proceed to the next set of calculations. In the second rotation, another 2 customers arrive, and they are fully boarded, bringing the total number of boarded customers to 4. The profit for this rotation is calculated as 16 minus the cumulative running cost of 10, which gives us a profit of 6. This becomes the new maximum profit, and we record the corresponding rotation as 2. In the third rotation, the last group of 2 customers arrives and is boarded, bringing the total boarded count to 6. The profit for this rotation is 9, the highest so far, so we update the maximum profit to 9 and note that it occurred in rotation 3. At this point, all customers have been served, and we return the rotation with the maximum profit, which is 3. This example demonstrates a scenario where all customers board within just a few rotations. Here, we have one group of 10 customers, a boarding cost of 6, and a running cost of 4. As usual, we start with all variables initialized to 0. In the first rotation, all 10 customers arrive, and we add them to the waiting queue. The wheel boards 4 customers, leaving 6 still waiting. The profit for this rotation is calculated as 24 minus 4, resulting in a profit of 20. Since this is the first rotation, it becomes the maximum profit, and we record the corresponding rotation as 1. The rotation counter is then incremented. In the second rotation, no new customers arrive, but we still have 6 waiting from the previous group. The wheel boards 4 more customers, leaving 2 still waiting. The total number of boarded customers is now 8, and the profit for this rotation becomes 40, which is higher than the previous maximum. We update the maximum profit to 40 and record the rotation as 2. In the third rotation, the last 2 waiting customers are boarded, and the total number of boarded customers reaches 10. The profit for this rotation is 48, the highest so far, so we update the maximum profit to 48 and record the rotation as 3. With no customers left, the process ends, and the rotation with the maximum profit, which is 3, is returned as the result. To understand the time complexity of this solution, we need to break it down into its components. First, initializing the variables like waiting, total_boarded, max_profit, max_rotation, and rotation is straightforward and takes constant time, or O1. Now, consider the while loop, which is the core of the algorithm. This loop continues as long as there are customers still waiting to board or if we haven't processed all groups in the customers array. In the worst case, the loop may run for n plus extra_rotations iterations. Here, n represents the length of the customers array, and extra_rotations accounts for additional rotations required to board all remaining customers after processing the input. For instance, if the total number of customers across all groups is s, the maximum number of extra rotations would be approximately CL, s/4, as the wheel can board up to 4 people per rotation. Combining these factors, the total number of iterations is bounded by O, n plus s/4, which simplifies to O, n plus s, where s is the sum of all customers in the input array. Now, let's look at the work done during each iteration of the loop. For every rotation, we add the number of arriving customers to the waiting variable, determine how many can board, and update the count of boarded customers. These operations, along with calculating the profit and checking if it's the maximum seen so far, all take constant time, or O1. Similarly, updating variables like max_rotation and incrementing the rotation counter are also O1 operations. Since each iteration involves only constant time work, the overall time complexity is determined by the number of iterations multiplied by the per iteration work. This gives us a time complexity of O, n plus s, where n is the length of the customer's array and s is the total number of customers. For space complexity, the algorithm is highly efficient. The input array customers requires O, n, space, while the auxiliary variables like waiting, total_boarded, and others take constant space, or O1. Since no additional data structures are used, the overall space complexity is O, n, dominated by the input array. Analyzing the algorithm further, we can differentiate its behavior across best, average, and worst case scenarios. In the best case, the total number of customers, S, is small, and no extra rotations are needed after processing the n groups in the customers array. Here, the time complexity is simply O, n. For the average case, some extra rotations are required to handle waiting customers, leading to a time complexity of O, n plus S. The worst case occurs when all customers arrive at once, such as in an input like S000. In this scenario, we need additional rotations to board all customers, with the extra rotations being approximately CL S/4. However, even in this case, the time complexity remains O, n plus S. Compared to a naive approach that simulates every rotation and explicitly tracks all states, this optimized solution is significantly more efficient. By focusing only on the current and waiting customers, it avoids unnecessary computations and scales linearly with the input size and total customer count. To mathematically confirm the algorithm's big O complexity, consider that the while loop executes O, n plus CL, S/4, iterations. Since the CL operation is a constant factor, this simplifies to O, n plus S. Each iteration involves constant work, so the total time complexity is O, n plus S, *1, which is O, n plus S. For space complexity, the input array customers takes O, n, space, while the auxiliary variables require only O, 1, space. Thus, the overall space complexity remains O, n. In conclusion, this algorithm is both time and space efficient, making it a robust choice for handling large inputs or scenarios with high customer counts. The linear scalability ensures that it efficiently balances performance even as the size of the input grows. When solving this problem, there are several common mistakes to watch out for. First, not accounting for remaining customers can lead to issues. For instance, if fewer than 4 customers are left in the queue on the final rotation, assuming the number of customers is always a multiple of 4 can result in incorrect profit calculations. This happens because the final profit depends on the actual number of customers served, not just the rotation count. Next, forgetting to handle edge cases, such as when there are no customers at all or fewer than 4 from the start, is another frequent error. Overlooking these scenarios can lead to runtime errors or incorrect outputs. Another issue is inefficient profit calculation. Some solutions recalculate the profit from scratch for each rotation, which dramatically increases time complexity. A better approach involves using cumulative sums or a rolling count to optimize performance. Lastly, brute force solutions often fail to impose limits on the number of rotations, leading to excessive computations or even infinite loops. Knowing that additional rotations eventually stop increasing the profit can help avoid wasteful operations. A subtle but frequent mistake is off-by-one errors when calculating profit for the current rotation versus the next. Misaligning these calculations can cause the solution to skip the optimal rotation or misreport the maximum profit entirely. From an interview perspective, it's important to recognize the underlying structure of this problem. The optimization revolves around managing a rolling window of capacity, specifically, the 4 seats available in each rotation. Techniques like cumulative sums, modulo operations, or sliding windows are often key to solving this efficiently. This problem also highlights a common pattern in queue and rotation-based challenges, the balance between brute force simulation, which is simpler to write but slower, versus optimized approaches that require additional logic. Be ready to articulate the trade-offs during discussions, such as how edge cases were handled or why additional rotations eventually become unprofitable. Demonstrating this type of analytical thinking can leave a strong impression during interviews. This problem shares similarities with several related challenges that you might encounter. For example, LeetCode 1829, which involves optimizing a running result, or LeetCode 621, where the task is to balance resource allocation over time, are both relevant. Additionally, LeetCode 189 focuses on efficient array rotations, while LeetCode 1011 deals with distributing resources over a limited timeframe. These problems help build intuition for scenarios involving rotations, queues, and resource constraints. When considering alternative approaches, brute force is the most straightforward. Simulating all rotations and calculating the profit for each is easy to implement but becomes computationally expensive for large inputs, with a time complexity of O, n squared. A more efficient option is the optimized rolling window approach, which dynamically tracks customers and profits as the window shifts, achieving O(n) complexity. However, this requires careful handling of edge cases. Lastly, mathematical optimization can be used to pre-compute results based on arithmetic formulas, offering high efficiency. While this method is less intuitive and demands a deeper mathematical understanding, it can be a powerful tool in time-sensitive scenarios. Great job! We've reviewed the problem, explored the brute force approach, and discussed the solution's key points. Remember, practice is key to mastering these concepts. Don't forget to like and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!